Hello everyone, in this video I'm going to show you one way to solve Einstein's Riddle puzzle using integer programming. So we consider 5 variables for every color. We're going to consider 5 variables for every nationality. We're going to consider 5 variables for every drink type, for every cigarette type, and for every pet type. So here's the detail of how we can program this. For example, if you look at the color blue, I have 5 variables, x11 all the way to x15. For green, I have x21 all the way to x25 and so forth. So if you count this way, you'll see that we're going to have 125 variables. I have a column here indicating how many variables are assigned to each color type or nationality or so forth. So like 1 to 5 variables will be assigned to blue, 6 to 10 to green, variable 11 to 15 is assigned to red, 16 to 20 variables are assigned to white, and so forth. Okay, so these variables are binary variables, meaning that they're either 0 or 1. For example, if x11 is 0, means the blue is not assigned to house 1. If x11 is 1, that means the blue is assigned to house 1. Likewise, if let's say x25 is 1, that means the green is assigned to house 5. And if x25 is 0, that means green is not assigned to house 5. Okay, so if that is the case, then we need to think about the constraints that we have to have for all these 125 variables. So one of the constraints that easily come to mind is, well, every house or every color is assigned to only one house. And if that's the case, then sum of these 5 variables for every type should be 1. Like sum of x11 to x15 should be 1 because blue is assigned to one of the houses. Or green is assigned to one of the houses, then sum of x21 to x25 should be 0. So for every type, we have to have this constraint. Another constraint we have is like for every house, we have only one color. So that means if I focus on house 1, which is this column right here, sum of these variables for only the color, that sum should be 1. So like x11, 2, 1, 1 all the way to 5, 1 should be 1 as well. Go to next column for house 2. Again, house 2 can have only one color, right? So then x12 all the way to x52 should be 1. So if you think about this as a matrix, then sum of the second column should be 1, sum of the third column should be 1, all the way to sum of the fifth column. So that gives us the second constraint. So like for every color, or maybe for all colors, we're going to have, for every row actually, we're going to have 5 constraints. For every column, we're going to have 5 constraints as well. So that this totally gives us 10 constraints for every block. Like for color, we're going to have 10 constraints. We're going to go nationality, the same thing. We're going to have 10 constraints here. Sum of the column in this block is going to be 1, and then sum of the rows is going to be 1 too. Okay, so these are the constraints on the variables that we chose, pretty much the integer variables, because these are all just 0 or 1. They cannot be anything other than these. And the next thing we need to talk about is the constraints of something like this. Like the first constraint is the British lives in the red house. Okay, so then how we can write this in terms of the variables we chose? So we have to come up with some equation that can indicate the house number based on the variables we chose, which are just binary 0, 1. So here's one example. If I want to pick the British house to be red, and let's go back to the British row here. So the British, or the nationality for British. So then in this case, we have x61 to x65. So one of these is 1 and all others are 0. So if I multiply these, by the column number, like x61 times the first column, which is 1, x62 times 2, x63 times 3, x64 times 4, and x65 times 5, this sum will pick up the house where British lives in, because one of them is going to be 1, and that is going to pick up exactly the j associated with that house. So going back to this equation, the left-hand side here picks up the house that British lives. The right-hand side picks up the house that is red. So let's go back to x3 row. So x3 is associated with the red color. So if I multiply j by each column and sum them up, that will pick up the house which is red. Okay, so then in this case, this is identical to the house that is red and should be equal to the house where British lives. So this should be equal, or if you bring both to one side, then the arithmetic sum is going to be 0. So with this idea, we can extend this type of constraint to other conditions, like Swedish keeps dogs. So the first part is going to be the house where Swedish lives, and the second term here is going to be the house where dogs are. The third constraint, Danish drinks tea. Again, the first term here is going to be the house where Danish lives, and then the second term is where the tea is drunk, right? So, and these should be equal. If you bring them on one side, that gives you this condition. So these are the equality constraints. Other constraints that could be a bit different is like constraint number 4 or condition number 4. Greenhouse is in the left of the White House. Again, we can use the same idea. The first term is going to be the left house, because j times x2j, this is going to pick up the house that is green. Again, the same idea. This is going to pick up the house that is white. And if the green is going to be on the left of the white, then the house number for green minus the house number for White House should be -1, because the house number for White House is 1 more than the house number for greenhouse, right? So then this sum should be -1. But this idea, I think the others are simply written, like owner of the greenhouse drinks coffee. Again, this is the greenhouse number. This is the house where coffee is drunk, and then the arithmetic sum should be 0 because they are identical, right? So these are the equality constraints. I'm not going to go over all the details, but you can extend this idea. I'm going to go over to a couple other things that could be different, like this one. Man living in the center house drinks milk. So this one is interesting. Like, if you go back to the variable list and look at x13, 3, so x13, 3 is, let's go back up here. So here. So x13, 1 to 5 are variable for house where milk is drunk, right? So then we're going to pick up the middle one, which is x13, 3. This is the middle column here, the column 3 in this block is going to be if milk is drunk in the middle house, and that should be 1. All other variables should be here 0. So that's why we have this constraint here, x13, 3 is equal to 1. Okay, similarly, Norwegian lives in the first house, so again x9 is associated with the Norwegian nationality, and then comma 1 means the first house. So first house should be the house where Norwegian lives, so that should be 1. Here's another interesting constraint. A man who smokes blends lives next to the one who keeps cats. So now this one requires a little bit of attention. So we use the same idea. So j times x16j. So this is, I think, the house where cigarette blends. Let's check. 16. 16, yes. This is the house where cigarette blends is smoked. So going back here, this is the column for blends. Let's go down here. Yeah, this is the column for blends. This is the column for the house number for blends. This is the house number for the cats. And if they're supposed to be next to each other, then the difference should be 1. So either 1 is on the left, let's say blend is on the left of the cats, or the cats on the left of the blends. So either way, the difference should be 1. So that means we have to take the absolute value equal to 1. Now in linear programming, this cannot be done because in linear programming, everything has to be linear, the constraints and the objective function. Well, so far we only talk about the constraints, so that cannot be done. So we have to extend this or expand it to inequalities. Okay, so that means this should be less than 2 and greater than negative 2. Okay, or we can say this is less than or equal to 1 instead of less than 2, and bigger than or equal to negative 1, or bigger than negative 2. Either way, I think it should be fine. So now we have inequality constraints. So far we had all equality constraints. Now we have inequality constraints. Okay, so we have a couple more of these inequality constraints like this one. Man keeps horses, lives next to the man who smokes Dunhill. Okay, so again the same thing. This is the man who keeps, so basically this is the house for horses, this is the house for Dunhill. The absolute value should be 1. Again, we expand it to inequalities between negative 2 and 2. Okay, so let me actually jump to how we really solve this. So far we only talk about the constraints. Okay, so now I'm going to talk about the objective function. The objective function is basically we want to maximize these inequality constraints that we have. Like for example, this one, we split this into less than 2 and bigger than negative 2, right? So we can actually bring this same thing into the constraint, into the objective function, and maximize it. So if you maximize it, then basically we are saying that the absolute value should be 1, right? If the variable or the term inside the absolute value is between negative 2 and 2, and we maximize the absolute value, then basically we are indirectly setting this thing to 1. So that's why our objective function is the maximum of all these 4 absolute value constraints. Remember, we had 4 absolute value constraints. One was man who smokes blends as a neighbor who drinks water, and then we had 3 more here. Norayan lives next to the blue house, and then man who keeps horses lives next to the man who smokes Dunhill, and then the last but not least is man who smokes blends lives next to the one who keeps cats. So we bring all these 4 inequality constraints into the objective function, and so we need to maximize this. But again, the objective function in this way in absolute value is not linear. So we have to linearize it, and to do that, we have to consider 16 cases. And in every case, we basically remove the absolute value and look at basically the variable inside. So this should be either positive or negative. We don't know which is going to be correct, so we're going to consider 16 cases. And I have the 16 cases. Well, by the way, these U's are the sum of the house number for every constraint we had up there. Okay, so the 16 constraint or the 16 cases we're going to look at is basically we remove the absolute value and look at whether the variable inside is positive or negative. And based on that, we write the objective function, disregarding the absolute value. For example, here I had a tree that shows, for the 4 constraint, for the 4 inequality constraint, what are the 16 cases? Okay, like U1 greater than U2, 3 greater than U4, 5 greater than 6, and 7 greater than 8, which means all of those constraints that we saw before, these 4 constraints, so that means each of these absolute values is positive, so we can get rid of the absolute value. Okay, and then so then our objective function turns out to be something like this, maximum of all these. Now this is completely linear. We solve this, and if we hit the maximum of 4, right, if you hit the maximum of 4, then that means this case is really the case. So we're going to run all these 16 cases, and then once we find the objective function to be 4, basically that's the solution, because then all of those should be 1, all of those inequality constraints should be 1, right? And so that should be the solution if the solution is unique. So in the next video, I'm going to talk about how we can solve this or how we can program this in MATLAB. So stay tuned and thanks for watching.